Welcome to EPG Pathshala lecture series on computer science. In this module on data analytics, let us continue discussing about generating association from frequent item sets and how these frequent item set generation algorithms may be modified for the purpose of accommodating voluminous data set. So, the objective of this session is to understand the computational challenges in deriving association rules and to know about alternatives and extensions or modified approaches for a priori methodology. Identifying frequent item sets and the computation model related to it will work like this. Fundamentally, the data will be kept in flat files rather than in database system. Now, when you want to access these flat files, you will have to access the disk and then you will have to generate the baskets, or sometimes the data may have been organized already into baskets. Now, every basket will indicate small set of many items, and when you expand the baskets will be expanded into pairs or triples or sometimes by user defined formats. So, now all that we need to do is we need to make use of k nested loops to generate all sets of size k. So, for example, here in this diagram you have set of items, the items are saved in a flat file environment. Now, the items are associated with say a value which is say the frequency count, which is a positive number. So, the items are positive integers and the boundaries between the baskets are going to be -1. So, you will have to access through these list of set of items and then generate the item sets, the frequent item sets. So, how are we going to address the challenge? So, the computational model which is used for generating frequent item set actually has two important issues. One is whenever I want to access the transactional data, it is available in my storage environment. So, the cost for mining here, that is to generate the frequent item sets and to derive rules from the frequent item sets, you need to access the database or the flat file environment. So, it depends on the number of input output task, disk input output task. Actually speaking, this algorithm can be executed in passes, that is you will have to read all the baskets and then this has to happen in turn. So, therefore, the total cost may also be considered as the number of passes which is taken by the algorithm over the existing data. So, either it depends on the number of disk input outputs or it depends on the number of passes which the algorithm uses for the purpose of working on the given data. Let us first understand the first issue, which is working with the memory, main memory. In any computational environment, we know there is a limitation for the main memory. So, when I am going to generate frequent item set, initially I may require all possible combinations of item sets. So, within the main memory you always have a limitation in terms of generating the number of item sets. So, as we read the baskets, we need to count the frequencies of these items too. So, what happens is actually speaking, you are not alone reading the items, you are also reading the frequency associated to those item. Therefore, you are dealing with a pair of information. One is the item itself indicated by its number or ID, and the other one is the frequency of these items. Therefore, when we think that we have main memory to accommodate say 1 lakh items, we are actually not dealing with single items, we are dealing with pairs of information about the item. Therefore, only half of the memory will be used for the purpose of holding items and the remaining half will be used for the purpose of holding the frequency associated to these items. In other words, only half of the items will be loaded into the main memory. So, now what happens is we sometimes also need to deal with the entire data set. Therefore, swapping in and out of the main memory will come into picture. Now, how many number of swappings depends on the total number of items that has been generated. So, with respect to the limited main memory, it may be really challenging when you are dealing with very voluminous data set. So, when you are generating the frequent pairs, what may be the issue that will come into picture? The hardest problem here is finding the frequent item pairs, that is I2, I1 or I1, I2. Now, frequent pairs are actually common, but frequent triples becomes rare, and furthermore frequent 4 item sets, frequent 5 item sets, and then frequent kth item set becomes very rare. Sometimes it may not even be part of your database. So, our probability is identifying the frequent pairs that are in common. To identify items that are in common, that is the pairs of items, we will have to generate first all possible item sets, and we need to keep track of the count of only those item sets that is at the end turn out to be very frequent. So, when you want to make use of the a priori method, naive approach, what exactly you are trying to do is you are trying to read the file once and then you are counting in the main memory with respect to each and every occurrence of the item pair. Now, what happens is for each basket which comprises of n items, we are actually generating n into n minus 1 by 2 pairs of item sets. So, you require a pair of loop for identifying one item and the other loop for representing the second item in the given pair. Now, this naive approach sometimes may fail, because if you are going to generate n into n minus 1, it is of the order n square. In case if n is so large, then n square will be very large. So, you may not have memory to hold the n square combinations, which will sometimes exceed the main memory. Therefore, it may be very difficult to handle a database which comprises of very large number of items or products. Let us take a scenario. Consider Walmart, assume it has say 10k items, sorry 100k items, or consider another scenario where say for example Google, which is dealing with 10 billion web pages. Now, here 10 billion is the number of items, similarly 100k is the number of products. Suppose if you are going to have these products or web pages represented by its count, the item itself will take say for example 1 byte of memory, and the count, since it is going to be an integer, assume it is going to have 4 bytes. So, put together for an item to be represented using its ID as well as its frequency, that is the integer value, you require 5 bytes. So, put together if there are 10 to the power of 5 items in the given scenario, then the number of pairs of items that may be generated will be n into n minus 1 by 2, which is 10 to the power of 5 multiplied by 10 to the power of 5 minus 1 by 2, which is 5 into 10 to the power of 9, and you are going to make use of 2 bytes. So, it is going to be 2 into 10 to the power of 10, 20 gigabytes of memory is essential. Now, when you take a look at 20 GB of memory, sometimes we may not have this space for holding the entire set of items that has been generated. So, now when you want to overcome this, you will have to think about how this information may be presented to the algorithm, and is this presentation effective. There are actually two possible approaches by which you can present the items and the possible combinations of these items. The first approach is a matrix approach, and the second approach is a triple or a record approach. In the matrix approach, you will be having the counts of all pairs of items represented in the given matrix, and in the triple or record method, you will be having 3 attributes, one indicating the first item, the second attribute indicating the second item, and the third attribute indicating the count of this item pair A and B. Suppose if the count is going to be represented by 4 byte. Then for the matrix, every cell will comprise of 4 byte information. But in case if you are going to make use of say the triple or the record approach, then for every information assume for the item you use 1 byte, therefore, you have 2 bytes for representing ith item and the jth item, and for the count you require 4 bytes. So, totally 6 bytes are essential. In certain scenarios, if it is going to be an alphanumeric information, we may require 4 bytes for representing an item itself. So, 4 into 3 attributes, totally 12 bytes are essential for representing one information. Now, you will have to decide when this may be used, whether the matrix approach or it is going to be the triple approach. When you are going to make use of the matrix approach, you can understand from the given matrix only one half of the matrix need to be computed, because the other half is going to be the same as the first half. The reason is, if I am going to have a cell represented by the index I and j, let us assume I is 1 and j is 2. Now, the index 1 comma 2 is going to indicate an item pair 1 and 2. Now, the reverse of it is 2 comma 1, which is also once again going to represent the same item pair. So, in the matrix it is enough if I can deal with one half of the given matrix. So, I may end up with a triangular matrix, and in this matrix every cell will be associated with 4 bytes. But if it is going to be a triple, I may not know how many such triples may be essential, but when advantage 1 may be good, when advantage 2 may be good. Suppose if the number of items that is going to be frequent is very high, number of items here in the sense the item pairs, then the matrix approach may be good, because many possible combinations of item pairs will be easily mentioned in the matrix, and the corresponding counts can be easily fetched for computing the frequent item pairs. Here in this scenario, the second approach may not be effective, but the other way, if you look around, if the number of frequent item pairs are going to be less, then if you are going to make use of the matrix approach, you will end up with many sparse information. Sparse here in the sense you will have many zeros in the given matrix, highlighting item pairs that are not even frequent. So, in such scenario approach 2 may be very good. So, when I am going to have very less number of item pairs, then I will go for approach 2, and if I expect more number of frequent item pairs, then approach 1 will be good. Now, let us take the a priori algorithm and understand how the issues or challenges may be overcome. A priori algorithm, as already discussed, will happen in 2 phases or 2 passes. Pass 1, you are going to read the baskets and count in the main memory the occurrence of each of the respective items. It actually requires a memory that is directly proportional to the number of items available in the given transactional data. In pass 2, you are going to read the basket again and once again count in the main memory only those pairs where both elements are going to be frequent, that is the elements which you have identified as part of pass 1. Now, this requires memory which is proportional to the square of frequent items only, for the purpose of holding just count alone. Now, if these 2 passes are going to happen, then you may find in pass 2 the number of items and hence the amount of memory, the quantum of memory which you are going to make use will be less when compared with pass 1. Now, if you are going to visualize this, that is the main memory during the execution of a priori algorithm, in pass 1 you are going to have all the items and their corresponding counts, and in pass 2 you will be generating the frequent items from these item sets, and then you will be having the counts of these pairs of frequent items which will be considered to be the candidate items for the next iteration. Now, if you are going to make use of this approach, generating the candidate items as mentioned in this diagram and then using it for the next iterations sometimes may be difficult. The reason, the frequent items that are generated here need to be once again mapped to the original database for identifying its count. So, instead if these frequent items can be represented by new numbers or if it can be mapped to their old item numbers, then generating the frequent item pairs and the corresponding counts will be very easy. So, the triangular matrix approach which we discussed earlier may be used here for the purpose of saving enough of memory when you are dealing with such scenario. Now, the same a priori approach, if modified, how it may behave for the purpose of accommodating voluminous data. In other words, how you can make a priori scalable. Now, one important thing which can be observed as part of pass 1 is the quantum of memory which is used in pass 1 is very less, indicated by this blue color rectangle. The rest of the space is going to be wasted or it remains unused. So, the idea here is, can we make use of this ideal memory? So, during pass 1, is it possible to make use of this ideal memory and then use it for indexing the frequent items that are generated? So, how this can do is using a hash table. So, for each bucket all that we need to do is just keep the count and not the actual pairs. These actual pairs must be associated to the hash bucket. So, the algorithm how it is going to be modified is, we are going to introduce one more loop for each pairs of item apart from each and every item which has been used as pass 1. So, now what is that you are going to do here is, every pair of item that need to be generated from the input file are actually not going to be part of the present file. So, we are actually speaking not interested in the presence of a pair, but we are interested in seeing the need whether the item pair should be part of the sample space or not, that is whether it is associated with say my support count, whether it satisfies with the support count or not. Now, the second important observation that can be made from say the a priori is, the bucket with that contains a frequent item pair is surely going to be a frequent set. Therefore, what is that we can do is, instead of holding that bucket with the set of items, we can just keep track of the total count in the bucket, and all that you need to do is verify whether the given count, that is a total count, is less than s, which is the support count or not. In case if the total count of the bucket is going to be less than s, then every set of item pair in the given bucket is going to be not frequent. So, as part of pass 2, only you will have to make use of those item pairs whose count is greater than s. In other words, you are going to make use of these item pairs and hash them to frequent buckets. Now, what may happen between the passes? Suppose if you are going to replace the buckets by bit vectors, that is you are going to have a bit vector, that is a binary vector, which will have a value 1 in case if that particular item is frequent, else it will be represented by a value 0. So, I am going to map each and every item pair to this bit vector, indicating whether it belongs to a frequent bucket or not. So, now what happens is, instead of working on the count which is represented by a 4 byte information, now we are reducing that to say a single byte information, which is almost 1 by 32 of the memory is going to be used. So, we are minimizing the quantum of memory which is going to be used in between the passes. So, in pass 2 what happens is, all that we need to do is count all possible pairs of ij that meet the condition, that is the frequency condition. In case if I and j both are frequent items, then you are going to hash this pair I comma j to a bucket whose bit vector is set to 1, else this item ij, if it is not frequent, that is if both the items are not frequent, then it is going to be hashed to a bucket whose bit vector is going to be equal to 0. Now, if both the conditions are going to be satisfied, only then it will work out. So, the objective here is both conditions are essential for the pair to have a chance of being frequent. So, if you revisit the same main memory using this approach, during pass 1 the memory that was underutilized or not at all utilized now is being used for constructing the hash table for every pair of frequent items. So, apart from the item counts that is generated, you are going to generate the frequent items. For these frequent items you are going to have a bitmap, and this bitmap will be mapped with respect to the pairs of item from the hash table. So, you take every pair of item, give to the hash function. If the hash function maps it to a particular vector, a bucket that is represented by a bit vector which is also frequent, then that particular bucket will be set to 1 and the corresponding item will also be placed into the bitmap. So, here as mentioned previously, the counts of candidate pairs will always be there in the pass 2. Now, when we are dealing with respect to the main memory, buckets also require few bytes for the purpose of holding additional details. Now, this is once again going to increase the cost here in the sense the computational time. So, the number of buckets is in the order of the main memory size. So, during the second pass what happens is a table that comprises of item I, item j and the count, which is a triple, is essential. Therefore, in this scenario we cannot make use of the triangular matrix approach, because when you are going to make use of a hash table, already we have mentioned only 1 by 32nd of the memory is going to be used. So, we are approximately going to eliminate 2/3 of the candidate pairs, and therefore, this modified approach will be very effective when compared with the naive a priori approach. What are the further refinements that may be done using this multi-stage approach? One important thing which you can do is you can limit the number of candidates that need to be counted. Now, how you can determine the number of counts is, as discussed in the previous session, we can make use of metrics like maximal or closed frequent item metrics for the purpose of determining whether you can pass the given item set or an item pair to the next level or not. So, when we are thinking about the first pass, we should also remember that there is a bottleneck with respect to the memory. Therefore, you will have to identify only those item pairs as part of pass 1 and then qualify, and only the qualified item pairs must be passed to pass 2. Now, when you are doing so, you will be bringing in one more phase into the existing approach. So, you require 3 passes over the given data, because during, that is, in between the passes you may end up with say false positives, that is, few pairs though they are positive sometimes may not be considered. So, that will be coming as an error, and in order to eliminate this error you need to introduce the third pass. So, this refinement algorithm, when visualized in the form of a diagram, you can understand during pass 1 the item counts are generated, the frequent items from these item sets are identified, then you are going to create a hash table. From this hash table you are going to map the frequent item pairs to the binary vector bitmap 1. Now, all the frequent item pairs hashed to this bitmap vector will now be passed to the next phase. Before passing it to the next phase, you will have to construct the second hash table. The second hash table will be mapped to another binary vector, that is bitmap 2. Now, whenever an item, say item pair I comma j hashes into hash 2 function, if and only if it is going to be frequent, then it will be passed to phase 3, that is, it will be mapped to the corresponding bucket in the bitmap vector 1. During pass 3, the count pairs I comma j will be considered if and only if I and j both are frequent and I and j hashes to frequent bucket in the binary vector b1, and then I comma j hashes to another frequent bucket in the binary vector b2. So, an item to be frequent, you are having 3 levels or 3 passes, and during the 3 passes the false positive can be eliminated and accordingly only restricted number of item pairs which are frequent can be passed to the next iteration. Thereby the total time taken for generating the item pairs will be very minimal, and also effective search of the item pairs can be done. During the multi-stage, that is as part of pass 3, as mentioned earlier, you will have to consider the 3 conditions. The first condition is both item I and j must be frequent. Then using the first hash function h1, the item pair must hash to a bucket whose bit is set to 1. In other words, it has to be hashed to one frequent bucket. Then using the second hash function h2, the same item pair must be hashed to another bucket whose bit vector is set to 1. In other words, it must be hashed to a bucket that is frequent. So, some important points that must be remembered is you require 2 hash functions, and these 2 hash functions are going to be independent of each other. Now, we need to check whether both hashes on the third pass. In case if it is not happening so, then we would end up with counting pairs of frequent items that hashed first to an infrequent bucket, but happen to hash second to a frequent bucket. So, you may end up with say a false positive. Now, how this may be refined? Now, the objective is instead of working on independent hash functions, you can make use of dependent hash function, that is more than one independent hash functions and hash tables in the first pass. But what may be the drawback is when you are working on multiple hash functions and hash tables, half the number of the buckets comprising of the pairs of item sometimes may increase in terms of the average count, sometimes it may be even double the average count. So, we may need to be very careful, and we should see to that you have enough of memory to hold this. If this happens, we can get a benefit like multi-stage, that is you will not bring in an intermediate state and then resulting in 3 phases. Instead, you will have only 2 passes. Now, when you take a look at this working methodology, you will find the item counts as part of pass 1 in the main memory, then the frequent items will be generated. After generating the frequent items, using the first hash table, you are going to hash the item pair to a bucket that is frequent or to a bucket whose binary vector is equal to 1. Secondly, the same item pair once again will be applied to the second hash function and then hashed to one binary vector or a bucket whose binary vector is equal to 1. In other words, it is going to be frequent. So, now as such, when you take a look at the memory, you will find only pass 1 and pass 2 coming into picture. Thereby, the existing a priori methodology works out very effectively even for very large item pairs. Now, when you are dealing with such modified approaches, you can also think about, is there any other way by which the number of passes may be reduced? In other words, can I have frequent item set generated in less than 2 passes? Yes, this can be done. That is, when we are looking in for less than 2 passes or fewer than that, then we may sometimes miss few of the item sets. This is going to be a drawback, but still then we are going to miss only a few, but majority of the frequent item sets still can be captured. So, what is that you can do is, you can actually have a main memory mapping like this. You can have a space separately for counts and then copy of the sample buckets. Now, what is that we are trying to do here is, we are going to apply random sampling method for the market baskets. That is, you are going to run an a priori on one part of the main memory. So, what actually you are trying to do is, instead of performing multiple input output tasks, you are going to restrict the number of input output tasks, but you are going to increase the number of items in the given memory. So, what happens is, to identify more number of frequent item pairs, you will have to reduce the support or the threshold factor. So, when you reduce the support threshold proportionately, then you will end up with matching sample sizes. Here, one important drawback is, you may once again end up with a false positive, but this can be avoided only during phase 2, that is pass 2. But here in our approach, we are looking in for an algorithm that works in less than 2 passes, that is only 1 pass. So, we are allowed to work on a smaller threshold. Sometimes the threshold can even be 1/25th of the existing threshold. So, this will help in capturing more and truly frequent item sets, but when you are doing so, that is when you are reducing the support by a larger value like this, you may require more space because it will introduce more number of candidate frequent item sets for multiple passes. Another approach is, instead of working on one bucket, I can repeatedly read small subsets from a given basket and then place it into the main memory and then run the existing a priori algorithm. But here we are not sampling, instead we are reading the same basket more than once. So, multiple input output task will come into picture, but this approach when compared with the random sampling approach sometimes proves to be effective because all possible frequent item sets can be generated, which is not possible in the previous, that is random sampling approach. The same approach when visualized, you can think about how it may be distributed, that is having the data distributed in multiple nodes and then running the a priori algorithm parallelly on all this distributed data, thereby it will result in say a distributed version of the a priori algorithm. So, to summarize, a priori approach has its own limitations. The limitations sometimes are associated with the main memory and also with respect to the time taken for executing the task and generating the number of item sets. Few of the extensions of a priori actually explore these challenges and they in turn reduce the number of frequent item sets that are generated for the next iteration, and handling such approaches increases the scalability of the algorithm, thereby makes the same a priori algorithm work for even a very large data set. Thank you.